take a look at these metal blocks. Now, what is really interesting about these blocks is they're all made out of different materials, and you can see that's evident from the colour. That is almost certainly brass. This one is copper. What the other ones are is anybody's guess. I think that might be aluminium. But here is something very interesting. They've all been cut to exactly the same size, and yet some of these feel really quite different to other ones of these. Now this one and this one, number 1 and number 7, they feel different in their weight. So what I want to do is use the laboratory balance to show that actually their mass is different. So let's have a look. Right, well, let's give this a go. Number 1 was 22 grams. And where was that number 7? There we go. 90 grams. Isn't that amazing? This material has more mass in it than this material, even though they are the same size. This is just heavier. Now we describe that as having a higher density. So density measures the amount of material, or the mass, within a certain size, or volume. Now, the calculation for working out density is as follows. So density is equal to the mass divided by the volume. I can work out how dense an object is by measuring the mass and measuring the volume. So what units are we going to measure those in? Well, here we have choice. The first way that we could measure it is in the following way. If we measure mass in grams, like you measure mass in chemistry, for example, and if we measure volume in centimetres cubed, which, as we'll find later, is equal to 1 millilitre when you're talking about fluid volume, then we would get density in the units of grams per centimetre cubed. But if we chose instead to measure our mass in kilograms, and our volume in meters cubed, then we would end up again calculating density, but this time it would be in kilograms per meter cubed. Now you need to be able to use either of these. Just be aware that we're still measuring density independent of what units we choose to measure it with. Now, in a formula, we might want to represent these 3 quantities with letters. Let me show you what those letters are. Mass is measured with an N. Volume is measured with a V. And density is represented by the symbol rho, the Greek letter rho. This can be used for rearrangement purposes. Now, rearranging 3 variables is really quite simple. I could have the mass is equal to, well, to get mass by itself, we must multiply both sides by the volume. So density times volume. Or, alternatively, if I wanted volume, then I would know it is mass divided by density. Now let's have a look at measuring the density of some regular shaped objects. So first up, I'm interested in this. I want to know how big this is. So I'm going to use this digital vernier caliper to work out exactly how large this is. And in millimeters, it's 20.20 millimeters. Now if I'm trying to find the volume of this little cube, and one of the side lengths is 20.20 millimeters, then I know that's 2.02 centimeters. The volume of the cube is length times width times height. And these are all going to be the same because it's a cube. So 2.02 times 2.02 times 2.02. That would give us 8.2401. But the important thing is we don't have to include all of those numbers. Let's just round it up and we get to 8.24 centimeters cubed. That's the volume. Now the next thing we need to find is the mass. So the mass is 90 grams. So if the mass is equal to 90 grams and the density is the mass divided by the volume, or the mass of 90 grams divided by the volume, 8.24 would equal there. Well, let's go with that. That might not be that right, but the units would be grams per centimetre cubed. And so I've now figured out that this material has a density of 10.9 grams per centimetre cubed. But what about this? This is a cylinder. Well, I can still work out the volume of this because I know a formula for a cylinder. Let's give it a go. This is 30.15 long and has a diameter of 9.95. It has a mass of 19 grams. So let's work out the density of this. Now, for a cylinder, the formula that gives the volume of a cylinder is the height of the cylinder times pi r squared, the area of the circle at the top. So if our height of the cylinder is about 30.2, then it's about 3.02 centimeters. The diameter was equal to 9.81 millimeters, so 0.981 centimeters. In this formula, we could do 3.02 times by pi times by, now we haven't got the radius here, we've got the diameter. So we're going to have to do this diameter and divide it by 2 to get the radius. And this is going to equal the volume, which is equal to about 2.284. Now I've cheated, I've already worked it out on the calculator. Centimeters cubed. So this is how we could do it for a for something that is the shape of a cylinder. But there are other shapes that we could do it with, just knowing the formula for those shapes. What about a sphere? We could work out the volume of a sphere with a formula. I could just apply the formula for thirds pi r cubed, and therefore work out the volume of a sphere. Check this out, folks. It is a glass pyramid. Now, there's a formula for pyramids, and there's a formula for most regular shapes. It doesn't matter what the shape is, so long as it's a regular shape, I could always work out the volume, and I could always work out the density. So what about this? This is the Philosopher's Stone. It's the only one known to exist. My good old friend Nicholas Flamel gave me this. Now, it's very difficult to take a measurement of. See there, it is wider than there. In fact, this is not a regular shape. There's no way I could measure the volume of this by taking some of its dimensions, because it's an irregular shape. So, to be able to work out the density of this requires us to find the volume some other way. Now, Archimedes found that way. He realised as he submerged himself into a bathtub that the water level rose. The more he went under the more the water level rose. He was displacing it with his volume. If he just measured how much ran over the edge, he'd find an equal amount of water to the volume of his body. And we can do that with one of these. This is a Eureka can. Basically, it's a bathtub for strange objects. If I put water in here, up level with the spout, and then I put the object within, then the water's going to overflow, exactly as much water as this object has displaced. Let's give it a go. So here I have filled the Eureka can up with a water level with the spout. I'm going to use a measuring cylinder to catch the runoff. Now I've got to be really careful here to make sure I catch all of it, so I'm just going to put it at an angle because I think it will spurt out quite fast. So I submerge the stone, and then eventually I let it go, and I want to catch every last drop that is coming out, because that is going to be equal to the volume of the stone. Now look at that, it's gone off the top of the flipping scale. Wait, hang on, I have a bigger measuring cylinder here. Haha, there we go. Why didn't I think of that? So, I get down on a level with it to measure it. I can see that it is 59 millilitres, which is equivalent to 59 centimetres cubed. The next thing I need to do is find the mass of this. Now ideally I would have weighed the mass before I got it wet, but I hadn't thought about that, had I? Got it. Right, now I'm going to try and dry this off, because it needs to be really dry, and this is why you should really work out the mass before you get the object wet. I'm going to put it on the laboratory balance, and they're 183 grams. So the mass of the stone is equal to 183 grams. Now, the density, therefore, being mass divided by volume, is going to be 183 divided by 59. And that is equal to, on my calculator, 183 divided by 59 is 3.1 grams per centimetres cubed. So there we have it. We now know the density of the Philosopher's Stone. Now, density is intrinsic to the material. What I mean by that is this material has the density of what we found it to be. It doesn't matter what shape or size we have cut this material to. For if I had a cuboid of material like this and found its density, if I then cut it in half, I would find that each half still had the same density. But how could that be? There's now only half of it. Well, the mass has halved and the volume has halved. So if they're both halved, then the ratio of mass to volume is still the same. The density does not change because I cut this material. In fact, I could use the density to identify material if it was unknown.